It is recording. Okay, so you guys can see my screen also, correct?
Yes.
Okay. So today I had to. So this is why I waited. People are still joining. Okay, so welcome to the third week in this course on Introduction to Machine Learning, and in this week, as it was in the NPTEL course, the main topic was the main topic was dimensionality reduction, and PCA was taught. I think yesterday. So today I'll be talking about the other variant that was taught in this week, which is called linear discriminant analysis. So it's a supervised version, or it does dimensionality reduction, but not in the same way as PCA does. So I'll talk about that, and then we'll, as I was asked by the by the NPTEL people to work on some questions. So I'll work on 3 questions. They will be pretty simple ones, and yeah, so that is the agenda for today. And the other thing is, like, today I had to work out a bit of maths to make you people understand about LDA, which is why, but I don't have a tab with myself, and hence I wrote it on a notebook and have attached the screenshots of, or the scanned copy of that in the presentation. So if you have any problem at any point understanding what I have written, or any point is unclear to you, you can just stop me and ask right away. So I'll start with the presentation. People are still joining, so maybe I'll switch back and forth. Yeah. Okay, so the first thing is for linear discriminant analysis, the first thing that we need to know is a very preliminary view of linear algebra. So the preliminary topics of linear algebra is one thing that I think everybody, all of you will know, is the basic element is a matrix. So if it has 2 rows and 3 columns, then the shape of the matrix is 2 cross 3. So that I think everybody knows. The other topic that will be required is for LDA is the topic of eigenvectors. So a vector V is said to be an eigenvector of a matrix A if AV equal to lambda V, where lambda is a scalar constant, and lambda is called the eigenvalue of A corresponding to the eigenvector V. So these are the this is the only definition that you will be requiring for understanding what is LDA. And so a very simple question is, can anybody say whether so suppose if I have eigenvector and eigenvector of V with a eigenvalue of lambda, then what should be the shape of A, in the sense that can it be a 2 cross 3 matrix? Can somebody unmute and say?
Can you come again, please? Could you come again, please?
Yeah, so let's say I have a matrix A which is 2 cross 3. So can that matrix have an eigenvector?
The presentation, yes.
I did not get the first part. You said yes, before that you said something.
Whatever we are looking at this on the screen, that kind of matrix is there.
Yeah, so that is a different, so that is just an example of a matrix. So let's say if you have a 3 cross 2 matrix, or rather a 4 cross 3 matrix, can it have an eigenvector, or can it, it is not possible for it to have an eigenvector.
It should be a square matrix.
Okay, so yeah, so that answer is correct. So from what is written on the screen here, can you understand why it should be a square matrix? If you don't have the idea, then you can tell me, I will explain that. It will be a hand wavy explanation, but you will be able to understand it. So
yeah, sir, please explain.
Yeah, okay, so let's say the equation of AV equal to lambda V is the defining equation for an eigenvector eigenvalue pair, correct? So let's say I have A is 2 cross 3 and V is a 3 cross 1 vector. Okay, is everybody with me? Anybody has any problem, you can stop me and ask me right away. So again I repeat, let's say A is 2 cross 3 and since you are multiplying A with V, V has to be and since V is a one dimensional vector, let's say, so V has to be 3 cross 1, otherwise you won't be able to multiply it with A. Okay, so what will be the dimension of the vector AV on the left hand side? A is 2 cross 3 and V is 3 cross 1. What will be the dimension?
2 cross 1.
2 cross 1.
2 cross 1. So the dimension on the left hand side is 2 cross 1. And what is the dimension on the right hand side of lambda V? What is the dimension of V in this case? As I said,
3 cross 1.
3 by 1.
3 by 1. So lambda V is the dimension of lambda. Lambda is a scalar. It's just 1, 2 something. So what
3
is?
by 1 only.
Yeah. So the
3 by
left.
1.
So the left hand side has a dimension of 2 cross 1, and the right hand side has a dimension of right hand side has a dimension of 3 cross 1. So by simple rule of dimensionality matching, you can understand that the equality cannot hold, and therefore A has to be a square matrix. Only if A is a square matrix that the dimension of AV and V will be retained, otherwise that equality cannot hold. Am I clear?
Yes.
Okay, so this is the defining equation of the eigenvectors, that AV equal to lambda V, and I just wanted to give you a brief of, I mean, this is the smallest possible overview of eigenvectors, but using this we will be able to understand about LDA. Okay, so let me come to the main problem that we are trying to solve. My handwriting is legible, right? You can understand what I have written on the screen, what I have put on the screen. Okay.
Yes. Yes.
Okay.
Yes,
So-
yes.
Okay, so for this, so with this background, we'll look at the problem of linear discriminant analysis. If you have if you have a chance to look at PCA, the first thing that you will understand, the first thing that you will learn is PCA is unsupervised. So the linear discriminant analysis, on the other hand, is a supervised dimensionality reduction method. So why do we call it supervised? We use the class information that is already there in the problem, that is given to us as part of the classification problem. We use that class information to retain the class discriminatory information as much as possible. Now what do I mean by that? So first let me just, I'll talk about two class LDA only, because that will bring out all the nuances of LDA in itself. So let us assume that we have m dimensional samples. So m dimensional samples means x1, x2 up to xn are all vectors of certain dimension. They can be 3 dimensional, they can be 10 dimensional, they can be 1000 dimensional as well. So so there are n such points, n such samples, out of which n samples belong to class 1 and n2 samples belong to class omega 2. Okay, so n1 plus n2 is equal to n. Now from this m dimensional space you want to project to, let's say, 1 dimensional space. So as there are two classes, so the another thing about LDA is, if you have C classes in your problem, then the maximum dimension or the minimum dimension that you can get down to is C minus 1. Sorry, the maximum dimension in this case. So if you have, let's say, 2 classes, the maximum dimension that you can get down to is 1 class. If you have 3 classes, you can get down to this you can get down to a 2 dimensional space. That is the rule of LDA. So in this case, let us say that I have n points x1 to xn, each of m dimensions, and from this m dimensional space I want to project all the points to a 1 dimensional space. That is the aim of LDA. For that I need a weight matrix that is denoted by W and y equal to W transpose X. So is anybody here who does not know about transpose of a matrix or a vector? You can please tell me now. I will, because I will use this extensively. So if you have any doubts about transpose, you can tell me.
Yeah, sir. Can you repeat transpose also once?
Yeah, so let me go back to the previous slide, to the first slide. So you can see A, right? Ravinder, yeah, you can see A, right? Which is 2 cross 3. So
Right.
so if you take a transpose of A, the columns of A will become the rows of A, of the transposed version of A, and vice versa. So it will become, the first row is 1 2 3. So in A transpose, the first column will be 1 2 3 and the second column will be 4 5 6. So you just take the rows and make it into columns. That's it. So
Got it, sir.
so the dimension becomes, so what will be the dimension of A transpose in that case?
3 cross 2.
3 cross 2, correct. Okay, good. So that is the very simple definition of what a transpose does. So in this case, now my question would be, if y is one dimensional and x is m dimensional. If you see here, x is m dimensional, as I said, it's a m dimensional samples. So if I take a particular sample and x is m dimensional and y is one dimensional, what is the dimension of W transpose? You see, I am multiplying W transpose and x to get y. Y is one dimensional, x is m dimensional, x is m cross 1. What is the dimension of W transpose?
1.
One dimensional.
One, it should,
One
it
cross
should be 1.
one.
1
It should be
cross
1 cross m.
1
M.
cross m, correct.
Yeah.
Yeah, so W transpose is 1 cross m, which means that W is of the same dimension as x. Okay. W is the same dimension x. So one thing which, I mean, of course this is not a linear algebra class, but whenever you have some doubts about what or whether to put a transpose or whether to do something or not, you will face these doubts multiple times whenever you learn linear algebra. So the first thing that you would that I would suggest you to do is to look at dimensions on the two sides of the equation. In most cases it will suffice to just look at the dimension of the two sides of the equation. So in certain cases you will be confused even after that, so for that you will require some advanced knowledge, but for now I mean for this case actually you will just require the dimensions of the both sides. Okay, so now coming to the diagram below, I know it's not very clear, but so I have the points, the dots and the crosses. I hope you can see them. So the dots are there and the crosses are there, and there are two, and these are two dimensional points, and I want to get them to a one dimensional line. So one dimension means it's a single line that I want to project them onto. So I have drawn here two candidate lines, line 1 and line 2, and I have projected the crosses and the dots on both of them. So which one is better according to you? So which one would you prefer, line 1 or line 2?
So it
Line
looks
1.
line 2 because line 2 looks, no, it's not line 2, it's line 1. Sorry.
Okay.
Should be line 1 because
See, any line where these points will be departed from each other would be easier to read. I mean dots versus crosses.
Correct. So which one do you feel separates the two dots and the crosses better?
x1, line 1,
Why?
because it gives us the complete separation between these dots and crosses.
And in line 2?
In crosses overlap with each other. When we are mapped to the single plane, they overlap each other.
So sir, if you have drawn these lines as like shown in the picture, then line 2 looks more better because they are like more giving more better separation from each other.
So what is your answer then, line 1 or line 2?
Line 2.
Okay. Somebody was saying line 1 gives a better separation. So why do you think line 1 is a I mean I wanted to say it out loud basically, that why you are preferring line 1 to line 2. You have said that it is separating probably line 2 just by looking at it, it's separating them out properly, but do you have any, let's say any mathematical measure as to why line 2 is better than line 1? Can anybody think, I mean anything, I mean whatever you are thinking you can say out loud. Why line 2 is a I will say that line 2 is a better option, but now can somebody say why line 2 is a better option?
Sir, the distance from the line 2 and the points may be high, so we prefer line 2.
You are on the right track. Yeah, don't unmute yourself. Yeah, so you are on the right track. What you are saying is the distance on the line 2 is more. So how do you measure I mean what is distance according to you in this case? I mean which point distance are you talking about?
Sir, the distance between the point and the line, sir. The line perpendicular to the point, sir.
Okay, yeah, so okay, so
Actually,
yeah, continue.
sir, actually, we can draw a perpendicular line from the point to the line 2, sir. It is the shortest distance between the line and the point. So, by comparing to line 1 and line 2, the point is very close, very farther from line 2, sir. So we prefer line 2. I think.
Yeah, you are
but
more or
maybe
less correct.
Sir,
Yeah.
sir, there was one concept we read, I guess, wherein like classes should be aligned in such a way that their distance should be maximum and the points within them should be minimum.
Correct. Yeah, so the first point that you said that the distance between the classes should be maximum. How do you denote the distance between the classes in this case? I have 5 points for both the classes. So how do you denote the distance between the classes?
So there was another thing which was told, that was centroid. Like if the distance
Correct.
between their
Correct.
centroid is higher, that means
Yes,
like they
yes.
are separate.
Yes, so that is the point that I wanted to hear from you all. So yes, okay. Yeah, so the final thing that I wanted to tell here from this diagram was so in order to denote the distance between the classes or to denote the separability between the two classes after doing LDA, what you need to look at is the mean of the points on that particular line. So you take the 5 points, you project it on line 1, you take the 5 points and project it on line 2 also. Similarly, you do it for the other class, and then you take a mean of those 5 points on the projected lines, I mean on line 1 and line 2, and you will see that the distance between the means is much less in line 1 and it will be much more in line 2, because line 2 the separation in itself is much more, and which is why you would prefer line 2 as compared to line 1. Am I clear, or anybody of you have any doubts? I can go through this again, because see, this intuition is the most important. The maths will come. Yeah.
You are calculating mean out of this for these lines. What do you mean by mean means? Why? What you are calculating actually?
Yeah. So these lines. So these lines after getting projected onto line 1 and line 2 will have some xy coordinates, right? So I don't know what the xy coordinates would be, but there will be some xy coordinates for each of the points once they are projected to line 1 and line 2. I am just summing up the x values, dividing them by 5. I am summing up the y values and dividing them by 5 to get the mean of the 5 points. So it's just summing them up. It's an average of the 5 points after getting projected onto the lines. That is what I am referring to as the mean.
Got it.
Okay. So so that is the point that we want to maximize. So this intuition is something which is the most important in LDA, and so there is one more thing, one more catch to this. I'll come to that later. And so basically what you want to do is you want to project it onto the lines in which the means of the corresponding classes are as far apart from each other as possible. So that is our aim in LDA. Okay, so now coming to the maths of it, so the measure of separation is the separation between them, is the distance between the two means. So let's say I have the mean in the x feature space is something which is quite simple. I just add up the points. X in this case is not referring to the xy x coordinate in the xy plane. It's just x is a m dimensional sample, as I had introduced here. So assume we have m dimensional samples. So x is m dimensional in this case. X is a point that we are talking about. So for all the points belonging to a particular class, we sum them up and divide by the total number of points in that particular class to take the mean of the points in the x feature space. In the y feature space, what do? We do similarly for all the x points. We have already projected them onto the y feature space and we sum them up and divide by ni. So how do we define y? We have already defined y in the previous slide. It is given by w transpose x, and x belongs to all of the points on the belonging to that particular class. W transpose doesn't have any x involved in itself, so I can take the w transpose out of the summation, and w transpose by 1 by ni summation of xi. So basically it's a linear combination of this is also known as a linear combination, that w transpose mu I, where mu I is the mean in the x feature space. So it's basically w transpose mu I. So whatever mu I had got in the x feature space, which is m dimensional vector, the mean, and I take a w transpose to that as well and get the mean in the y feature space. So my possible objective function, the objective function that we just said, was j omega. Let's say it's jw, w because w is the vector that we are trying to find, and it is mu1 bar minus mu2 bar, which is the difference of these two means, the difference of the two classes, that mu1 bar is the mean of the first class, mu2 bar is the mean of the second class, and therefore the w transpose of mu1 minus mu2 is the objective function. So let's look at these two examples, that mu1, that these are the two classes and they are separated out, and let's say my two candidate what should I say, the planes or the lines, two candidate lines are the x axis and the y axis, so they are projected. Mu1 is projected onto the y axis and mu2 is also projected onto the y axis, which leads to better class separability here. And similarly mu1 and mu2 are projected onto the x axis. However, in this case you see the distance between the means is larger than the corresponding distance between y. Am I clear at this point? Does anybody have any question, or is everybody okay with this? Can you understand that that when I am trying to increase the distance between the two means, x axis is where I should go rather than y axis? Is that understandable to everybody?
So again, from the picture it looks correct, but here is a question, like how are you identifying this x and y?
No, so that I will come to later. I am just saying that let's say I have these two examples. Is this point clear, that this is that mu1 and mu2, that x axis leads to a larger distance between the means than y axis? Is this point clear?
Yes.
Okay. So till now my objective function is I want to separate out the means as much as possible. So if my two candidate options are the y axis and the x axis, then whatever I am trying to do right now, I will obviously choose the x axis because it is a larger distance between means. But you see, once I project the points onto the x axis, there will be some overlap between the two classes. Can you see that? If I project these points, I mean, let's say the points of the class 1 are distributed according to the ellipse with the center of mu1, and the points belonging to class 2 are distributed according to the ellipse with center mu2. When I am projecting them on x axis, then there will be a overlap between the two classes. Can everybody see that, or any doubts?
Yes, very much. We can see that right portion of the mu1 is looking to be falling on the left
portion of mu2. However, if you see that if we are projecting them onto the y axis, then that does not happen. that is also clear
Correct.
from this figure. So, this shows that when I am just trying to separate out the two means, that is not probably the correct thing to do, because in this case it would lead me to a projection on the x axis, whereas where my original objective is to separate out the two classes, y axis would have been a better option than x axis. Okay. So, that is why I drew this figure here to give you an intuition as to why just separation of the two means may not be enough in all cases. So, what do we need to do? We need to figure out the spread, as somebody said before, that we need to figure out the spread between the spread that is present in both the classes. Like mu2 is spread much more along the x axis, it is spread out much more along the x axis than the points in class 1, which is why when I am projecting on x axis they are overlapping, because the class C2 is much more widely spread along the x axis. However, the spread of mu1 or the spread of the two classes are similar if not equal across y axis, which is why projecting them on the y axis is leading to a complete dissociation of the two classes. So, the spread of the points for a particular class across its mean is something which is known as scatter. It is also known as variance. So, that is something that we need to take into account by doing this analysis. So, the solution to this is maximize a function that represents the difference between the means. However, at the same time it is normalized by a measure of the within class variability. So, this is something that Fisher came up with. There might be other ways of doing this also, but Fisher came up with something, and this is from then on it is known as linear discriminant analysis. So, for each class we define the scatter. This is also the definition of variance, is given by SI bar square equal to y minus mu I bar whole square. So, what it is giving? It is saying that you have a point and this is the mean. Tell me how farther away I am from the mean and sum them up across all the points in the particular class. Okay. So, so somebody say please that among class C1 and C2, which one has a higher variance in this figure?
mu2, class 2.
Correct. So, class 2 has a higher variance. So, that is so the objective function of linear discriminant analysis as given by Fisher was mu1 bar minus mu2 bar, which is the difference between the two means. I take a square of them and I take the summation of the variance of both of them, which basically means I normalize them by the variance. I normalize them across, I normalize them by the variance of each class. So, the top the numerator is also known as the between class variability, and the denominator is known as the within class variability. Okay, so now these are all scalar. The definition that I gave here, y minus mu I bar whole square. So, that is the definition when the y and mu I are all scalar quantities. In this case, we are dealing with vectors, and for the vectors we have a corresponding definition of variance, or which is also known as covariance. So, it is just a definition like SI equal to where x belongs to omega I, which is belonging to a particular class. I take a x minus mu I, which is a vector, which is a m dimensional vector, and again I multiply that with a transpose of that same vector, which is x minus mu I transpose. So, if x minus mu I is m dimensional, it is m cross 1, x minus mu I is x minus mu I transpose is 1 cross m, and multiplying them together will give me a m cross m matrix. So, basically SI is a m cross m matrix, and it is also known as the covariance matrix, and it is only applicable when we are dealing with vectors. So, with that definition in mind, let us now come back to the how we are denoting this SI bar whole square. So, SI bar whole square will be W transpose x minus W transpose y mu I whole square. Y is, as we saw, is W transpose x, and mu I bar, as we saw, is W transpose mu I. So, W transpose x minus W transpose mu I whole square, and this on being broken down gives us W transpose into x minus mu I into x minus mu I transpose W. This is from the definition of the covariance matrix, and this becomes W transpose Si. This should be Si square actually. This becomes W transpose SIW. So this is the SI square that we are talking about, S1 square and S2 square. So correspondingly what we do is and the numerator also becomes the mu I bar minus mu 2 bar whole square, and this becomes W transpose SB into W, where SB is defined as mu 1 minus mu 2 into mu 1 minus mu 2 transpose. These things are like it won't be very clear to you because this comes from the definition of multivariate. So these are all multivariate expressions, and when we are talking about vectors, instead of scalars, so this is the way we define. So don't think too much into it, just look at the different expressions that I have written, and yeah, so this is W transpose mu 1 minus mu 2 into mu 1 minus mu 2 transpose W, which becomes W transpose SBW, and this summed up over the two classes becomes W transpose SB W transpose SW into W, where SW is basically S1 square plus S2 square, or yeah, so S1 square plus S2 square is given by SW here. Okay, so with that, okay, hope I'm recording. Yeah, okay, yeah, why is this not working? Okay, so we have W transpose SBW by W transpose SWW, and we need to maximize it. Okay, because JW is mu 1 square minus mu 2 square and S1 square plus S2 square, so we need to maximize the difference between the two means, which is normalized by the sum of the variances or the covariances in this case. So so we get we take a partial derivative of j omega. Anyway, it's just a single derivative, so partial derivative becomes the actual derivative. So del j omega by del w is equal to 0. Setting that, we have to set out we have to give W transpose SBW by W transpose SWW, and we take a derivative of that and set that to 0. Okay, somebody, I mean, I know this is not very clear to all of, may not be very clear to all of you, but can somebody tell me the dimension of the numerator or the denominator, or both of them? What is the dimension of W transpose SBW? Let's say W is m cross 1 and SB is m cross m. What is the dimension of W transpose SBW?
M cross M I something.
Okay, let us look at it.
1 cross m.
Okay, any more answers? Any other answers? Okay, let us look at this. What is the dimension of W? Can somebody unmute?
1 cross M. 1 cross M.
No, the dimension of W is m cross 1. W is being I mean, if you can see here, right? Yeah, y equal to W transpose x. So x is m cross 1, y is 1 cross 1. So W transpose is 1 cross m, which means W is m cross 1. Okay.
Can you please repeat again?
Yeah, okay. What is the dimension of x?
M cross M, no?
X is m cross 1. Okay. X is m cross 1. What is the, and y is 1 cross 1, because I am projecting onto a one dimensional space. So y is 1 cross 1, x is m cross 1. So what is the dimension of W transpose?
Cross M.
W transpose is 1 cross m. So what is the dimension of W?
M cross 1.
Okay, correct. Okay, so now here I have W as m cross 1, correct? You can see my cursor, right? Or it is not visible?
Yeah, sir. W is m cross 1.
1, okay. What is the dimension of SB? SB is defined as mu 1, okay. Mu1, what is the dimension of mu1?
mu1 was lambda x, right? Lambda.
Mu1 is just the average of all the points in X
Class 1.
Scalar.
Class
of class 1. So what is the dimension of mu1?
Should be m cross
1
1.
by
then?
m. 1 by m. 1 cross m.
It is the average of all points which are of dimension m cross 1.
So it should be m cross 1 only.
It should be m cross 1. Okay, so mu1 is m cross 1, mu2 is also m cross 1. So what is the dimension of mu1 minus mu2 into mu1 minus mu2 transpose?
Cross m.
It will be
1 cross m.
see, what is the dimension of mu1 minus mu2?
M cross 1.
What is the dimension of mu1 minus mu2 transpose?
1 cross m.
So when you multiply, what is the dimension that you get?
Square matrix of
Okay, square. There is a square.
Correct. So that is a square matrix of m cross m. So SB becomes so SB becomes m cross m. W, as we saw, is m cross 1. So what is the dimension of SB into W?
M cross 1.
M cross 1.
M cross 1. What is the dimension of W transpose?
1 cross m.
And when you are multiplying this, what do you get? What is the dimension of the numerator?
Scalar.
It's a scalar.
By 1.
Okay.
1 cross 1.
1
Yes.
cross 1.
Yeah.
1 cross 1.
Correct. So it's a scalar finally. Okay. So we don't need to. I mean I I went through all this, but finally, if you see this sort of thing, like if you have a matrix, this has to be a square matrix. Otherwise, you won't be able to multiply. When you are multiplying square matrix on the left hand side with a vector transpose, and again on the right hand side with another vector transpose, the final result will always be a scalar. Okay, so that is a rule that you need to understand. I mean, it's pretty simple. If you just look through, if you just look at each component separately, you will understand why this should always be a scalar. Okay, so when you are taking this, so by basically you are taking the derivative of this with respect to a vector. So there are certain rules here, but right now what I am doing is I am taking a simple derivative, so that, I mean, it's just like you just treat this normally as like we treat derivatives. So W transpose by the division rule, W transpose SW, W comes here, and I take a derivative of the numerator, and minus W transpose SBW, and I take a derivative of the denominator, and I set it to 0. Yeah.
One second. Why we are taking a derivative? What is the need for taking a derivative? Can you explain once?
Yeah, I want to maximize JW, correct? Because JW is this function where it shows the difference between the two means. So when I am taking the derivative of JW, my ultimate aim is to work out the maximum value that JW can achieve. So for that I am taking the derivative. Okay.
Okay, but
Yeah.
actually, derivative, when we are derivative means that is we are finding minimum difference, right? Then how can we find the how can we maximize the function?
Yeah, so you want to maximize the difference between the two means, correct? That you want to maximize mu1 minus mu2 whole square.
Right. Yeah, I got it.
So if you are trying to maximize this, you will take a derivative of this entire expression, and this expression I am denoting by JW.
Yes.
Okay.
Yeah, thank you.
Yeah, okay. So I am taking the derivative. There will be a square term at the bottom, but that won't be 0. I can assure you that, but I am not going into the details why that won't be 0, and so I am ignoring that for now. And I am just taking the numerator once I have broken this derivative down in by the division rule, and I get this expression that W transpose SWW, and taking the derivative of this, this is, you can treat this like a square. This W transpose SBW, you can treat this as a square. So because of that square, this 2 term is coming, and finally this will be SB into W. Again, this comes from linear algebra, and I am not going to the details of that, so that is the way this entire thing works. Like SB into W, and this 2 comes because of the square, and similarly this becomes 2 SW into W, and the rest of it remains as it is and equal to 0. So from here what I do is I divide this entire expression by W transpose SW W, and that is not a somebody is trying to join now. Yeah, and that is non-zero, that is a non-zero quantity, and I can divide them, and I cancel the 2 out from both the sides, and this becomes SBW equal to W transpose SBW and divided by W transpose SWW into SW into W. So this is just rearranging this equation, and then what I do is I take a inverse of this matrix SW. SW is again a matrix of dimension m cross m, and I take a inverse of this matrix and I put it on the left hand side, and this SW goes away, and W transpose SBW by W transpose SWW is nothing but the cost function that we wanted to maximize in the first place. So basically what we have got is we have got a matrix into a vector equal to some scalar quantity into that same vector. I mean, except for how I did the derivatives and everything, this equation is clear to all of you, is it? I mean, does anybody have any doubt at this equation?
So, sir, only one doubt. When you say you have notionally added square, so is it because why did you add square? Like, that's what my question is.
Which one?
Because of which you added 2, like line number 3 from the bottom. You introduced 2 because of square.
Yeah.
So where is the square? I can't see in this.
See, first of all, I mean, so W transpose SBW, okay, this particular thing that you are seeing, W transpose SBW, that is basically the linear algebra equivalent of taking a square, okay. So I can't go into much more details about this because you don't have the necessary background, but basically how can I say, okay. Okay. See, if SB, for example, this W transpose was not there, okay, only SBW was there, and if you had differentiated with respect to W, then you would have got just SB. Now you are multiplying, so you are multiplying that same matrix on the left as well as the right with the same vector W, and then you are taking so it's like saying that okay, so that square is because this is a linear algebra equivalent of taking a square. This is a bilinear form, and so taking the derivative of that is basically taking the so if you take a derivative of x square, you get 2x. So similarly, if you take the derivative of W transpose SBW in linear algebra in vector calculus, you get a derivative of 2 SBW. Okay. Okay. So so there is some background there, but so the easiest way that I can explain to you is like this, that just understand that this is the square form, and you have to take a 2 times, but anyway that 2 anyway is not mattering because 2 is there on both sides, but so the actual derivative of W transpose SBW is 2 SB into W. Okay.
Cool, sir. Cool. Thank you, sir.
Yeah. Okay. So till this.
Soumya, sorry to interrupt. Can I share my understanding of whatever?
Sure.
Yeah. Actually, sir, Ravinder sir, you are asking for the square, right?
Yeah.
Actually, SB, we are doing derivative with respect to W. So SB will be a constant. So we can take SB out, then it will be W transpose into W, right?
Mm-hmm.
So in vector, W transpose into W is nothing but W square.
You are not audible. Is it to me or?
I got your point, Raman. I got your point. Thank you. I think both of you have explained it. Thank you.
Okay.
Where can be?
I can't hear you properly. Is it just me or?
No,
So
sir.
yes, we have the same problem. So
Okay.
W transpose W क्या होगा? What will be the
W
output?
transpose W is the 2 norm of the vector W. So W transpose W will just be, so it's basically W square, so 2W. So you can consider it to be the W square term. It's actually the square of the 2 norm of W. So taking a derivative of that will just give you 2 times the vector, the same vector. Okay.
Okay.
Yeah. Okay. Yeah, so I understood what Raman was saying here. There is one small catch in that, like when you are taking the derivative, you cannot just take SB out of that derivative, because SB is within the W transpose SBW part. So the way that you have to do it is, you have to, so you will have to do a derivative of like W transpose, and basically you can break it up, W transpose SBW in a by the product rule. You can take W transpose, the derivative of SBW, plus W transpose, the derivative of W transpose into the SBW left apart. But again, that goes into vector calculus, so I don't want to go into those details. So so let's just say that the derivative of W transpose SBW is 2 SBW, and yeah, so that's it for now. Okay. Doing all those many juggleries, we get finally to the final equation, which is SW inverse SBW equal to JW into JW into W, where JW is a scalar, SW inverse SB is a matrix, and W is a vector. So when I had introduced eigenvectors in the first slide itself, the definition I had used was AV equal to lambda V. Okay. So here, if we think of these two equations, and if we see that A is the corresponding version of SW, or SW inverse SB is the corresponding version of A, W is the corresponding version of V, and JW is the corresponding version of lambda, then basically what we are seeing on the left hand side is the eigenvector equation of the matrix SW inverse SB. Am I clear?
Yes, sir.
Okay. So if this is clear, then is this statement clear? That's just, thus JW is the eigenvalue of the matrix SW inverse SV, and what we wanted to do was to maximize the value of JW. So the highest eigenvalue of SW inverse SV is the value of JW, the eigenvector corresponding to the eigenvalue, and hence the required vector is W. Am I clear?
Yes, sir.
Okay. Nobody has any doubts at this stage. Okay. So this is what is LDA. This is what LDA is all about. Okay. So okay, since nobody is saying anything, I will take it that everybody is clear at this point. So basically, so how do we do linear discriminant analysis? We take SB. SB is defined as W transpose, or SB is defined as mu1 minus mu2 into mu1 minus mu2 transpose. That is how we define SB. We define SW as follows: x minus mu I by x minus mu I transpose for each class and sum them up. We take this matrix, we compute this matrix as SW inverse into SB, and we take the highest eigenvalue of that particular matrix and get the eigenvector of it, and that is my vector, and that is the vector that we want to project onto. Okay, so that is all that is about there is about linear discriminant analysis. So I'll stop talking about this particular topic and move on to some questions now. If you have any questions, you can ask about LDA. Okay.
So sir,
yeah.
Highest vector means like the vector which will give you points which are maximal apart, like these two, the distance will be highest.
No. Highest eigenvector. I never talked about highest eigenvector. You see here I have written, as we want to maximize JW, the highest eigenvalue of SW inverse SV is the value of J omega.
Okay.
Okay. I look at the highest eigenvalue of that matrix and I take the eigenvector which is corresponding to the highest eigenvalue. Okay.
Okay.
It is also known as the most dominant eigenvector of a matrix. The eigenvector which is corresponding to the highest eigenvalue. We never say anything about because there is no such thing which is known as highest eigenvector or something. We always talk about the vector which is corresponding to the highest eigenvalue of SW inverse SB. That is the vector that we project on. Okay. So that is it. Any more questions on LDA? Okay, great. Now I will come to 3 questions. So these will be pretty simple. I don't know whether they are also, I don't think they are in the assignment, but anyway. Okay. There is one more topic that was taught in this particular week, which is KNN, K nearest neighbors. So can you all see the question on my screen, or should I read it out?
Yes.
Yes.
Okay, so basically you have a set of 8 points, you have a set of 8 points, and you are given the x and y coordinates of all of them and the corresponding classes. And suppose you want to predict the class of a new data point which is given to you, which is x equal to 1 and y equal to 1 using Euclidean distance in 7 neural net and in a 7 KNN structure, which means that I will take the 7 nearest neighbors of my particular point and classify it accordingly. So to which class, the question is to which class the data point will belong. So when you are faced with this sort of question, what is the first thing that you should go about doing? So can somebody answer that?
Filter out
Find
the
the
cases.
Euclidean distance.
You will compute
Filter out
the somebody is saying filter out or something. I am not properly hearing, but can
So, sir,
Euclidean distance we have to take, right?
Euclidean distance from?
calculate the distance from the prediction point.
Calculate the distance of the prediction point from
all the possible available near neighbors.
correct. Okay, so that I hope is clear to everybody. And so basically that is what I have already done here on the right hand side. If you see on the right hand side of whatever the line that I have drawn, I have mentioned the distance from the point which is 1 1, which is my prediction point, and I have mentioned the distance between of this particular training example from that particular point. So the first point will be 1 plus 1 whole square, 1 plus 1 whole square plus 1 minus 1 whole square, which is root over of 4, which is 2. The second is 1 plus the second is just, I think, root over the second is just 1, the third one is root over 2, and so on. So you are taking a 7 nearest neighbor, your KNN is 7, k is set to 7 in this case. So which are the, so there are 8 points. So which point should not be considered in the nearest neighbor classifier? Can somebody say?
the higher value, which are having the higher value.
Yeah, so which one among these 8 points won't be only 1 point won't be considered, because there are 8 points and I am taking a 7 nearest neighbors.
Minus 1 1 and 1 minus 1.
So root 5 should be not taken because it's the highest, 2 points on
2 2.
root 5, the last one, 2 3.
2 3. Yeah, somebody was saying that I will take only 2 points. See, you will take only 2 points if you are doing a 2 nearest neighbor classifier. In this case you are taking a 7 nearest neighbor classifier, so you will take the 7 nearest points, and out of these 8 points, which means only 1 point will go away, and that will be root 5. So I think Sarvinder answered. I think it is yeah, and it is correct. You will throw out the last point in this case, and so look at the distances. The 7 nearest neighbors will have the labels of so the 7 nearest neighbors will have the labels of plus, minus, and so on. So yeah, can somebody say which class the data point 1 1 will belong to? You can look at the first 7 classes and tell me.
1, 2, 3, 4. So
Minus.
Minus.
Correct. So
Negative.
it will belong to the negative class. So this is a pretty easy question. And next it's a bit theoretical, like about PCA, because I talked about LDA. PCA is
Soumya,
yeah.
Could you please come again? How you figure out the negative?
Yeah, you understood why I took this 7 points, right? Why I did not take the last point? Hello?
That I have so far understood.
Yeah. So if you are not taking the last point by nearest neighbor rule, what you need to do is you want to take the nearest 7 nearest neighbors and take a vote between them. So if out of 7 nearest neighbors, majority of them say that majority of them belong to one particular class. In this case, it will obviously happen because you are taking odd number of neighbors.
Yes.
So that is why in this case you see there are 4 negative classes and 3 positive classes. So majority is with negative classes, and hence you will say that 1 1 will belong to the negative class. Okay.
So if they were equally divided between plus,
You can't have equal division. You can't take equal division, right? Because you are taking 7 nearest neighbors. So that is why you will always take odd numbers. Okay, so that is it. Then question 2, since I talked about LDA, this is a pretty preliminary question about PCA. Like, which of the following is or are true about PCA? So there are 4 such points. Somebody say, you can look at the 4 points and can somebody answer this question? If you can't read, then I can read them out also. If you have any problems in reading. Okay, I guess it's legible to.
PCA is actually unsupervised method.
Only two.
2, 3, 4 all are looking correct.
Only
And that
two.
D.
2, 3 and 4. Okay. 2, 3 and 4 is what I think the majority of you are answering. PCA is truly an unsupervised method, so that is for sure true. I mean, that is for sure false. PCA, the first option is not there. So it identifies the directions that data have the largest variance. That is my objective in PCA. And maximum number of principal components is less than number of features. If that is not true, then PCA would not have been called a feature in dimensionality reduction method. If that is why the third point is also true. And all principal components are orthogonal to each other, which is I mean, if you work out PCA, you will find that all the so it's again I won't go into the details of it, but because of that, because of the way PCA is computed, all the principal components will be orthogonal to each other. So the correct answer is 2, 3 and 4, which is option D. Okay, so that is question 2. The last question.
What do you mean by orthogonal?
Orthogonal means perpendicular. It's just a fancy word for this thing, for perpendicular. Okay. Okay, so that is question 2. Finally, the last point is about question 3. When there is noise in data, which of the following options would improve the performance of the KNN algorithm? So what should you do? K means the KNN, the K in the number of nearest neighbors that you should take. When there is noise in the particular in the data, should you increase or decrease the value of K, or whatever you do won't change your answer? What should you do?
Increase value of K.
Can you come again? I did not hear.
Increase the value of K. Option A should be the answer.
Okay, does anybody have any other answer like B, C, or I don't know why D, why people will choose D, but anyway, B or C? Okay, then I would ask, why would you increase the value of K?
So sir, because if the neighbors which are there are not giving you the clear picture, you increase the horizon of that, find out more neighbors. So that you increase your space, and when you increase your space, you get more clarity of which one is the better.
Correct. What you are saying is very intuitive, so I like that. The other way is, I mean, another way of saying this is, I mean, basically what you said is correct. So if you are taking, for example, k equal to 1 and you are deciding based on that, or let's say k equal to 2, if there is a lot of noise in the data, when you are taking k equal to 2, it's very likely that both of them are noisy data. So you are basically classifying based on noisy data itself. When you are taking a large number of points, the chances of all of them being noisy comes down. So therefore it is prescribed that you take more number of neighbors when the data is noisy.
But won't the value of k results in increase in error of testing? Like initially it decreases and after a while it saturates towards increasing side. Won't that be the case?
I mean, yeah. So of course, if you increase k to such high numbers, then it would be a problem. But I am talking about if you are not increasing k to such, I mean, one possible thing is you can increase k to all the points that is there on your side. I mean, all the training points that you have. So that won't give you any good result. So of course it will start increasing after some time, but I am saying that what I am just trying to say is, if you have noisy data, then k equal to 5 or k equal to I mean, it's all relative, it's all depends on the data that you have with you, but generally taking a higher value of k will help you in that case, but of course not that higher value that your accuracy starts decreasing. So
maybe starting from the 1 value to 5 value it will benefit.
So you can continue increasing the value of k. Once your test accuracy or validation accuracy starts decreasing, you can stop increasing k at that time. Okay, so yeah, so that is the end of today's lecture. So what I did was I worked out, last day I actually I showed you an example, worked out example in Python about how to code, what did I show, decision tree. Today I had the similar plan of doing the same thing with LDA, but I was asked to do some questions, and so therefore I did some questions. So yeah, if you have any questions on LDA, or these 3 questions I think are self-explanatory, but if you have any questions on LDA you can ask, otherwise I will close the session today.
LDA will work on only on binary classifier, or it will be
no, for multiple classifiers it will work, but for multiple classifiers the formulation is slightly different. So basically what you need to do is, here you are separating out the means of the 2 classes. For multiple classes, what you need to do is you need to take a centroid of all the classes. So let's say if you have 3 classes and you need to take the centroid of all the 3 classes, and for the 3 different means you try to maximize the distance of the mean of that class with the centroid. Okay, so basically the centroid becomes a common point and you have 3 means around it. You want to maximize the distance between the centroid and each of the 3 means. So that is how you formulate the problem when you have multiple classes.
Is it applicable for regression?
Regression, W transpose X, let me see, W transpose X, mu 1 minus mu 2. Regression, I don't think it will be that applicable. Discriminatory classes, I don't think it will be. I mean, I've never seen it being used for regression. I don't know whether there are some papers on this, but I have not seen it being used for regression. Mostly it's used for classification.
Sir, in the exam, will the derivation of the
No. These things won't come. See, anything which requires linear algebra won't be there in the final exam, because it is not taught in the main course. What we are trying to do is, we are just trying to give you a flavor of, there is a lot of these things going on in the background behind everything that is being taught, like PCA, LDA, all of these things have a lot of linear algebra background things going on in the background. So our hope is, since you are exposed to both sides of this of a particular thing, after this course you will go ahead, and if you take some advanced courses, there you will learn all these things in much more detail. So this is just introductory course. So in the courses after this you will get a feel of all these things. There you will understand in more detail why in PCA all the principal components are orthogonal, for example. So that is a direct consequence of a linear algebra result. So but in this exam all those things are not required.
Yeah, sure, sir. Cool.
Soumya,
Yeah.
it's my request to
Yeah.
you to include the somewhat that Python notebook like at the end.
Yeah, so
Means we
that
are really
is
interested in.
that is there, but the thing is, the NPTEL people are telling me to get some questions done. So I can't really defy what they say, but I also know that that thing is much more useful to people and to practitioners. That is much more interesting to me maybe also, but I can't help it. I have to give some. I don't know. Maybe I'll. But otherwise, see, the other thing which I can do is I can just include a Python code and I can run over some questions, but that I feel would be very superficial. I mean, I just wanted.
No, whatever you are doing, that is okay. We are okay with that. At the end, 10 minutes if you are showing that kind of thing, we are really.
That is actually
we are
then.
playing,
Yeah.
playing around with that, and we are getting more out of it.
That is true. I mean, I know the last session also was. I hope it was helpful to all of you. Let me see, in the next lecture next week I don't think there is requirement of any Python coding, but again when logistic regression and SVM all those things will be done, maybe I will try to show some Python coding. Let me see, I will try to manage time properly and I will try to include that.
So there are plenty of sources available on net also, Professor, so maybe
Which one?
Sorry?
Yeah, I did not get what you said. I could not hear.
There are plenty of resources available online also. Sample codes are also available.
Yeah, sample codes are available. Like if you like all these things which I told today, they are also available outside. I mean, for machine learning, you will find everything which is there either in YouTube. Somebody must have done. I mean, this is. I mean, LDA is a technique that has been there for I don't know how long.
But learning from you is a charm, sir.
No, that is fine,
Yes,
but that is fine. But I mean, coding is something which I wanted to show you guys, because with that you will get some feel about how things are done. Let me see when logistic regression and SVM those things are taught. I will code one of them, one of the two in the class. Okay.
Soumya, one more question I have.
Yeah.
Why PC is so popular, but why LD is not that much popular, and what are the use cases and what are the limitations of LD?
Okay, LDA is not that much popular. Why? First of all, it's supervised. Okay, PCA doesn't require any class labels. So, so that is one thing. Okay, yeah, and the other important thing is, if you see here, like SW inverse SB, right? You can see this matrix SW inverse SB. Now, computing SW inverse, computing the inverse of any matrix is very computationally inefficient. So we generally don't want to compute SW inverse SB. So that probably is one more thing why LDA is not very popular. Yeah, so these two things might be the reason why it is not very popular, I guess. Mainly because it's supervised, and other thing is SW inverse SB and kernel LD, and so again I am going in. There is something called kernel is just a minute. Yeah, there is something called kernel PCA, which is, I don't think kernel LDA whether it is there or not there, but it is not used that much. So yeah, primarily because it's SW inverse SB, we don't want to compute the inverse of any matrix, and the other thing is it's a supervised method as compared to an unsupervised method for PCA.
Yeah, so this inverse is a very solid reason, very solid reason.
Yeah, inverse is one reason. I am trying to figure out, I am trying to understand or trying to think about why this is not used that much. Yeah, I think these two are the main reasons.
But of course, as the science evolves, new methods comes up.
Yeah, like PCA also is, I mean, there are some techniques which are not used. I mean, PCA also is not used that much today. I mean, dimensionality deduction is something which we do till date, but with the advent of deep learning, that has stopped being that relevant that much. Earlier it was very relevant when machine learning was there, but with the advent of deep learning, it has, the importance of PCA and all these things have come down.
So one more question, like final exam will be descriptive or objective? Like
that I am not sure actually. You can ask the TAs of this course. In the NPTEL course has assigned some TAs, so that I am not, they will be able to answer better. Yeah, any more questions?
No sir, thank you so much.
Okay, if there are no more questions, I'll stop this session. Again, I'll meet you next Saturday, 20th August. Okay.
Thank you sir.
Yeah.
Thank you.
Okay. Bye.
Thank you.
Bye. I'll close this session. Bye.